So we continue our lecture. So yesterday, so we already start at the disadvantage of the classical control, right? I just summarize what the last lecture we have done. So in the last lecture we already analyzed why so the lecture we already analyzed. So we have the classical control. So in classical control, so we the theory behind so for classical control, the theory behind is to be behind on the design on the characteristic equation, right? And the second is so we behind on the formulation of the second order system. And so we consider, so we why we can make the control design based on the classical system is we consider like the second order system, so we can have a high order system, right? So we do the approximation here, and so we can neglect this part, and by this approximation, so the high order, this is a high order system can behave like the second order system, but something in some case, so the approximation here is in some case this cannot, right? This cannot, and then this is the quickness of the classical control. So we want to eliminate this quickness, right? We want to eliminate this quickness, and because we want to eliminate this quickness, we have to come to this class, and this class is a modern control, right? So let's see what we can do next. So for the state modeling, so we already reviewed what is the state. So we consider in the time domain, right? And this is the state model. In this state model, this is the inner state model. This is the control input, right? This is the system matrix, right? From here, so if we already proved that so we already proved that Si minus A is the characteristic characteristic equation of the system. Right? And we also prove, because this is the for finding the root. So for finding the root of this equation, so for finding the equation, we found that the root of characteristic equation are the agent value of the agent value of A, right? So in this course, so we do not consider the this is the output. So the output, if we follow this equation, the output is have the two part. This part is the output including the state of the system and including the input of the system. In these courses, so we don't consider this one. We don't consider this one because we in this course we just consider the feedback control. Right. I will explain to you. So why don't don't consider this one. This is why if we consider the feedback control, we don't consider this part. Okay, so let's move to next slide. So this is the clock diagram. So if we follow this block, so we can see here. So the signal here will be E, U, right? The signal here will be from here to here. This is X. X is state of system, so this is the AX, right? And so we, if we consider this one can be becomes X dot will be equal to AX plus BU, right? And then for this part, so we can consider X, Y is equal to CX, and this schematic diagram is totally present a system in a state space model. So if we make to here, so we make our subsystem here, so we make here is plus D, so here we have the matrix D, so this is to become DU, and here the output is becomes CX plus DU. Okay. Okay, so here we see this is the, if we see the arrow from here is in the state of the system. The system will feedback to comparison with the output. This is the errors, right? And if we consider this loop, so we call this is the feedback, right? But if we consider this way, so this is go from here to here, therefore this is, we call this is not feedback, this is the feed for work, and this is feedback, right? And in this course, so we don't consider FIFO case, so we just consider the feedback case. Therefore, we ignore BU here. Okay. And then, so for the control design, so that is the system. This is the control design. This is the control design. Control design means so we have to okay. Here we want to we just focus on the feedback control, right? And this is the control input. And then so our control design is to calculate the U, right? Just that the output is come to ED. ED is the desired response. What is the desired response? So the ED, so we define the ED in the time domain. So this is Y. So ED means this is our YD. The YD is have to design the desired response means YD must be have the select time less than the select time design, have the overshoot less than overshoot design, and have the steady state errors at our requirement, right? So we have to focus on we provide the control law, the control input will provide Y until YD, right? So here, how we can calculate how we can calculate U, right? So in classical control, so we can calculate U. So we use the what? We use the dominant pole. But the point in using the dominant pole, we already have the quickness, right? So here we don't want to do that anymore. So how we can here we just develop new algorithm, right? And then they develop the new. This is they make the new feedback law, right? So in classical, we use the what? We use the lead like the exercise we did yesterday. We do lab, right? So here, and we can come up with the PID, right? So we already analyzed the quickness of classical. So we develop the new control design can be eliminate the quickness of the classical control. So we develop the new algorithms. So we have the formula like this. So we feedback. This is we feedback the state. Here Ex and X is a vector, right? X is the vector. So we have K is also the vector because we consider the this system is n order, right? N order will have the n state here. Okay, so we have the K. K is the vector. K is the length in the row vector until Kn. This is will be multiplied with is until Sn. And here we have the U. U will be K1, X1. So if we have the minus here, if we have the minus here, U will be minus K1, X1 minus K2, X2 until Kn, Xn, right? And here we have the formula. So because we must be plus with R. This is we have in this part because we if we multiply row vector with the column vector. So this is we have the number. So this one will have the number. One the number belong to R. R is a real set, the set of real numbers. So plus 2. This is capital R. This small r. And R. So we call this is R. R is the reference. The reference, right? Reference means what we want the system achieve. Okay, and here, and finally we have the control input in here. So just let's see what is so if we develop the control input like this, so we write the question rise is how effect of the new control input. Okay, so for answer this question, so we come to next slide. Let's just come to the next slide first, and then we come back later. So just because of our control input like this is the U, right? So if we substitute U to here, so we have this formula, okay? And here, so we have the new equation X A sorry. So we have here A minus B K X plus B K X plus and this one already removed, therefore this is this is x plus r, right? And then so we already talked about the state space model, and this matrix become the new one. The new we have the new parameter matrix. Okay, and with the new matrix, so we have the new Asian value, and then the new Asian value means we have the new root of the characteristic equation, right? So we can from the previous system, so we this is the previous system, we have the A is parameter. So by adding K, so we can have the new eigenvalue, right? And we have the new root, and we have the new root of characteristic equation, and we can have the new response of the system. So the new response system can be defined by K, right? By K, because if we changing K, so its K is changing, so the matrix also the changing, and by changing K we can changing the eigenvalue, and we changing the growth of the characteristic equation. Okay, and therefore so we prove in the root right? So if so, as we say in the dominant pole in the classical control, so we can have the dominant pole here. Right? We can have the dominant pole. This is the so let me do it more clear. So first we have the requirement. Right. From the requirement, so we can have the dominant pole. From the requirement we have from requirement, so we have the dominant pole, right? Okay, so here if in classical control so we can adjust this kind of, we can let the system have the dominant pole, but we also, because this is the high order system, so we can in the classical control the system still have an order pole. In classical from order poles, because we just order either in classical control, so order pole cannot be controlled, right? That is the weakness of uh, that's the thickness of classical control. So we developed the new algorithm is feedback control. And let's see how come the feedback control can control the audibles. How the feedback control can control audible, because feedback control the feedback control can control audible, so we can say that the feedback control can place all of the whole of the system. Okay, and let's see how the controller can do that. Okay, so here you see the ACE matrix. Okay, so if we take this kind of equation, so how the equation can work. So just follow my calculation. So we take the b multiply with k. So k is from k1 to kn, right? So this matrix can be if we multiply from this matrix to this matrix, what is the result? So this is uh, n 1. This is the 1, and so the result will be n up to n. So what is the result of pk? P multiply with k. So just take one rows multiply with one columns. Okay. So what is the result here? So the result here. So we can. So finally we will the 0 0 0 0 only k1 k2 until kn here, right? And if we take minus here, so the minus will appear like this, right? And then if we take a minus bk, so what is the result? So the k will appear in this part, in the final row of 8. If we take the a minus bk, okay, and here this is the abk. We take the k here, and if we calculate the determinants of this one, and the determinants this one will result in this is the characteristic equation of the form, and then we start to see the coefficient. So k is the n coefficient, k up to kn. K coefficient can be appear, right? So this is from k1 until kn, right? So therefore, so let's assume that this is this equation have the n root, right? Just note that n root, this root can be accepted in the complex plane, right? Not only the real plane, but complex plane. And if we changing k here, changing k, we just changing k, we can choose because of k appear in every coefficient of these polynomials, right? Therefore, we can by changing changing k. By changing k, so by changing k, we can change the root of the, we can change all root of the system, right? And the ability of now we can see how the k can be affected to all of the roots of the system. We already see the principle of the system, right? Okay, let's see next. Let's see. Uh, let's see how we can find the remaining question is how we can find the proper k. Okay. So I just stop here in 1 minute. Just stop here in one minute. So, and then you can image uh, how we can change the case already. Okay. So, and let's talk about the theory behind it, about the dominant pole. So for the perfect control, for the perfect control, so we need the system is have a two dominant pole. This dominant pole come from the desired response, right? And we also need other pole. Other pole is have the far away from the two dominant poles, so it at least 5 times, of the real part, right? This is what we what we need, right? And then so we have the new method here. So we just if we have the n order system, we just divide system in two parts. The first part is to second order system, and another part is other pole. This belong to other pole. But the difference between the feedback control law and the classical control is that this other pole we also can choose. We also can choose far away from dominant pole, and by combining two parts like this, so we have the given the risk pole pole placement, and by combining two this part, we already have the design. We have the new definition: design characteristic equation. So for the feedback control, so we can determine the second order system, the two dominant pole. We also can put other pole is far away from the two dominant pole, and we combining become the desired characteristic equation. Just remind you the previous slide. So in the previous slide, so we have ax pk, and we from here we already have the sn plus a1 plus k and here. So let's add, so let's here. Okay, so we already developed a new by adding, sorry, is it K? By adding K, so we already have the system. We can change the system, change the every coefficient of the the new system after we apply the feedback control law. So this is the Kn. We can adjust the Kn to have the this is this is the desired function. The desired characteristic equation is we can define here and already have the function like this. So that this function must be achieved by the system. Therefore, we just take the desired characteristic equation equal to the new uh, characteristic equation of the new characteristic equation of the system, and from we can make the balance of the two equations here, and from the this balance we can obtain the value of every k, and by obtain the k, so we can obtain the controller k u k is minus k is plus r. For detail, so we just take the example. So this is the plant. We already use the classical control, right? And we fail. Already. So now we didn't do classical control, so we can start to do the feedback control with the new controller u minus kx plus r. Okay. First of all, so we just we have the system. You see the system. We just this is the system x dot a is plus eu. Okay. This is the c. This is the y. So we just take x from here, multiply with minus k. This is the this O u minus k is plus r here, right? And we have to find k, right? To find the k, so we have to find the new characteristic equation of the system after we adding the new controller. And first of all, we have the transformation from transfer function to the state model like this. And we also select the nominal pole. But the difference between this method and classical method is we also can select the third root is 5 times less from the dominant pole. So the system is the first order, second order. So this is image. So we have the dominant pole is minus 4 here, is here, right? And if we multiply from here, multiply 5 times, means the third root is must be far away at least 5 times. So therefore we choose the first pole is minus 20. Okay, and so we just check the desired characteristic equation by multiply the second order system of this root multiply with the s plus n. And here we have the desired characteristic equation. And then so we calculate the new after apply the new controller. So apply the new controller. So here we have the new characteristic equation. And that thing already calculated in the last slide, and now we have this is the new characteristic equation. Right. And so the next thing is just we do the balance. And we do the balance between the characteristic equation, the new characteristic equation, and the new characteristic equation, and the desired characteristic equation. And from here we have the k, we can find the value k1 up to k3. And this is the results we already saw it. And let's simulate. So what is our requirement here? So the overshoot is 5% and the selling time is 1 second. And let's simulate it. So this is a 1.6. Actually, this is a 1.6 minus multiply with 10s with the exponent is minus 3. And here, so if we but if we check here, we see there's the overshoot. We can achieve the overshoot. Also, if we apply the 2% criteria, so we also achieve the TS is less than 1 second, right? So for transient response, so we already achieved the overshoot and set time. Okay, that is our improvement in comparison with the classical control of the feedback controller, right? However, here still have the problems here. I remind you. So the characteristic equation just can by place the deal with the characteristic equation. We only solve the problem of the transient response. But if we want to the system achieve the steady state error, so the characteristic system is not reflects the transient response of the system in the time. Therefore, we have to do more here. But that is not the problem. So we continue. So we already achieved the transient response. Our method already makes the improvement. So what is the steady state error? So here, because we apply the unit step, apply the unit step, right? if we apply the unit step to this system, so we the the actually if we want to study step error here, so this is must be row to 1, but this is not equal to 1, therefore we have to do more with the steady step errors. Okay, with the steady step errors, so let me remind you, so why we add in, if you do PID, so why we add in the interval, why we add in the interval, so we add our interval because we want to our control output to track the desired response, right? So from that strategy, so we also learn from that strategy. So if we here, this is the reference, this is our reference, right? This is our reference. Right? So we just modify this one. We just take another reference, right? So we compare the output with the reference. For example, this is our reference is unit step. We compare this one and we have the errors. And for the PID, because we have the interval, what is the role of the interval here? The interval here, so in the interval here, so if the why we do the interval, so the role, if we have the errors, even if very small, the interval will have this accumulate with time, right? It's very small. If it is very small here, this cannot drive the system, but it accumulate until time is the until the one time. This will be big, and this can drive the system. Right? This is the role of interval here, and we do the same strategy here. And then we put the interval here to accumulate errors, and this is to become the Sn, and Sn we name Sn is the virtual state, and with the virtual state we also multiply with the Ke, and we multiply with the Ke. Ke is the new control gain. With the virtual. Why this called the virtual? Because why this is called the virtual? What we call this is the virtual. Virtual is not virtual means it's not real, right? Why it's not real? Because it is a real system. This is the real system. This is my real system, and this in this part. So we can do this part in the computers. We can do this part in the computers. And in the computers, because we can program it by using the algorithm, so we can program it. Therefore, it's not real. This is just it's not real. This can be programmed. Therefore, this is the virtual. Although this is a virtual, this still can affect to the system, right? Therefore, this is we consider this is the virtual space. This is the state, really the state of the system, because this can affect the system, but this is not real. Therefore, this is the virtual state. Okay, so looking at in this diagram, so we have the state of the system and combine with the virtual one, and this is become a new system, let's see it become the new system here. And new system must be have the new characteristic equation. And if you have a new characteristic equation, and then the problem is, so if we have the new characteristic equation, this is the new characteristic equation, right? The new characteristic equation, we have the new pole. Here we already have the new pole. So we have the two pole here. We have the some pole. We already designed by using the feedback law, right? But by adding the integral, so we have the new pole. We have the new pole here. This is the new pole because of adding the integral. This pole could be affect to the system, right? Mm-hmm. If we want to keep the, if we want to keep the transient response, we want to keep transient response. So if we want to keep the transient response, so we need to don't allow the new pole affect to affect to the transient response of the system. Even the new pole, so by adding the integral, we can solve the steady state error, of course, but we have to don't let the new pole affect to the transient response. Therefore, this is easy to do if we just place the new pole is far away from the dominant pole. Therefore, we just choose the new characteristic equation, and the new characteristic equation so we have the second order, right? We have the order pole here, right? We already designed it in transient response. We add in the integral, we have this is the new pole, right? And the new pole, the new pole just far away from the dominant pole, right? And if we make like this, the desired characteristic equation already defined. We just do the balance of two of this one, and we already have the vector k, new vector k, and constant is k, where k is the contingent. K is not affecting to the steady state errors, but k is the contingent is the avoid the new pole affect to the characteristic of affect to the transient response of the system already defined in with the feedback control law, right? And let's simulate the system again. And okay, we already see the steady state error because we put the integral control here, right? We put the integral control here. The steady state error already achieved, the overshoot already achieved, and the overshoot already achieved, and the settling time also already achieved. Finally, already achieved 4, right? Okay, so I finished the lecture here, and I have the exercise put in the PK e-learning, and you can do this after this lecture. Okay, thank you.